All right, this is your nuclear chemistry, specifically nuclear decay video. Okay, in it we're going to talk about the different types of decay, as well as nuclear reactions in which decay occurs. Okay, so the first thing I want to talk about are the different types of decay, which are not that, whatever that is. Go this way. We have alpha particles. Okay, alpha particles have a symbol of alpha, or another way to put it, and it's 4 2. Okay, or we can say alpha particles are a helium nucleus. Okay, and you're thinking, well, that looks like scientific isotopic notation, and yes, it is. That's why we did isotopic notation before we did nuclear chemistry, because it's all about isotopic notation. Okay, the next type of decay is beta decay, which is really my best beta. Is really nothing more than an electron. Okay, so hopefully we should know what these numbers are meaning. Okay, but if not, I'm going to go over them because you've never seen a negative number down there. So we'll talk about that. Right? We have gamma decay. I'm going to do my very best mu, which is not that great, which is 0 0. Okay, and there's no other symbol for that. Okay, and then you also have a positron. Okay, and a positron is 0 1. Okay, so let's first break down this isotopic notation. Okay, here I have X, and I have A, and I have Z, right? X is referring to my symbol, in this case the element, so chlorine would be Cl, oxygen would be O. Okay, A is referring to the mass number, and Z is referring to the atomic number. Okay, nice review, easy. Now, your decay particles, okay, which what decay is sometimes isotopes are going to break down, okay, and they end up giving off radiation. That makes them radioactive. Okay, now understand that a vast majority of the isotopes that are present in this world do undergo some sort of decay over time. It's just sometimes the rate of decay is so large that we don't notice, and we often don't see them as being radioactive. But in fact, all isotopes have the potential to become radioactive and emit some sort of decay. And again, decay being one of these 4 types of particles. Okay, so let's go ahead and reevaluate the alpha particle, which is pretty much, like I said, a helium nucleus, which is composed of 2 protons and 2 neutrons. And how I know there's 2 neutrons is because 4 minus 2 is 2. So if you ever hear anything about alpha decay or something that's emitting alpha particles, okay, emit. Now this is I know this sounds weird, but some people always get confused. When I say something is emitted or it emits, that means it's being released and it's being let go. So if I say something is being emitted, and say an alpha particle is being emitted, or this process emits an alpha particle, that means this particle right here is being released, and it is a product of some sort of nuclear reaction. Okay. The beta particle, which I tend to just use this, is an electron. Okay, and the reason why we have the numbers that we do right here is because the mass number for an electron is 0 because there are no protons and there are no neutrons, so it's 0. Okay, and then the atomic number, which is usually a positive number to indicate some sort of element, in this case is just representing a subatomic particle, and that subatomic particle has a negative charge. And so we're going to indicate that since protons have positive charge and electrons have negative charge, we're going to indicate the atomic number, quote unquote, for a beta particle as a -1. Okay? Now, if something is emitting beta particles, that means these electrons are being released. Okay? There is another process known as electron capture. Right? Electron capture is when electrons are part of the reactant side, or they're going into the reaction. Okay? Now, I'm using words like reactant and product, so I just want to do a quick review. We have a reactant, or multiple reactants, and then this arrow occurs. This arrow is supposed to indicate some sort of change happening, and then we have products. Okay? So if I have electron capture, that means the electron's going to be found over on the reactant side of this arrow. Okay? If I have beta decay, or if I'm emitting beta particles, that means the electron is going to be on the product side. Okay? Is there ever a time when I'll say that we have electron capture and beta decay? Sure. As long as you understand what it means, I could make a whole bunch of gibberish up, and you should still be able to solve the equation and solve complete your task. Okay? Even though I haven't really told you what your tasks are yet, which I will in this video, if you can add and subtract, you'll be fine. Okay? And you know how to look at a periodic table and try to find the numbers. Okay? But like I said, I'll take care of you there. Your next step is going to be gamma. Now, I'm not even going to I tipped it one more time, and that's just ridiculous. So gamma, as you can tell, I have no mass, I have no atomic number. All this really is just radiation given off. There's no mass, there's no charge. It's a gamma ray. Okay, so it's a type of electromagnetic radiation that's being given off. Okay, you've all heard of gamma rays before, right? Incredible Hulk, right? Got absorbed a whole bunch of gamma rays and then turns into the Hulk, of course. But the next type of decay is called a positron decay. Now, positrons decay, they are, I know this sounds weird, but they are positively charged electrons. Okay? Now, there's not too much that we know about positrons. We just know that they exist. Okay? And they are essentially a different type of matter, and we're not going to go too far into that physics realm. All I really want you to know is that this is what a positron looks like, and if you know what a positron looks like, and I say if it's emitting a positron, then you know that I'm talking about this symbol. Okay? But like I said, positrons and gamma radiation are not going to be a huge portion of these worksheets or this test, but you should at least know what they are and how to use them. Okay? So, on to an actual example of what I would ask of you. Okay? So, let's say I had uranium-238. Uranium-238. Okay? Now, hopefully you look at this isotope and you should be able to give me the isotopic notation. Okay? Right? I know it's uranium, which is a U, and how do I know that? It's on the periodic table. Okay? You have to find it, which is, it's number 92, and then I put 238 right there. Okay? And I'm telling you that uranium is going to undergo alpha decay. Well, an alpha particle, so if it's alpha decay is going to be a product. If I mention decay, it's a product. Okay? If I say electron capture is not decay, but everything else is decay. So if it's decay, it's a product. So I draw an arrow. Okay? And it's an alpha particle. All right, so alpha particle is given off, but obviously I can't destroy. If I can't destroy or create matter, I cannot destroy or create the parts that make up the matter. So all these protons and neutrons must balance out. And really all that turns out, or really all that really adds up to do is I need to make sure that I have, XAZ, right? There's XAZ, there's my standard isotopic notation variables. I need to make sure that 238 equals 4 plus A. Right? So I'm looking just at these top numbers right here. That's what I'm looking at. Okay? And then if I do that, I'm going to end up with A equaling 234. Okay, oops, I wrote over it. 234. Okay, and then if I look at the other number on bottom, same idea. Actually, that looks like a 2. I'm going to make that a Z. There we go. I know that 92 equals 2 plus Z. So what does Z equal? Z equals 90. Right? Well, my 90, I can look at the periodic table and see that it's thorium. This would be the other product to the alpha decay of uranium-238. So I will be asking you to determine what are the products of this nuclear reaction. Or I might say, what is the reactant of this nuclear reaction? Okay, all it really comes down to is, can you do this? If you can do that, if you can add and subtract, you should have no problem with this. Okay? So, let's go and take a look at another one. But in this case, I'm going to go with a beta decay. So I have nitrogen 13, right? Nitrogen 13 looks like this, 13, 7, N, right? And it's undergoing beta decay. Again, decay is a product. Decay is a product. So arrow, and I write my electron, my beta decay, my beta particle, right? And then I'm some sort of some sort of product is also formed, right? Well, if I look, A should be equal to, or excuse me, if I was to rewrite it just as it's written, 13 equals 0 plus A. Well, that means A is 13. Same thing. 7 equals -1 plus Z. Right? So -1 plus Z equals 7. That means it must be 8. Right? I look at 8. I find 8. That's oxygen. Okay? So if nitrogen 13 undergoes beta decay, oxygen 13 is also produced. Okay? Straightforward. Now, hopefully we realize that if I have gamma, right? These are both zeros. They're not going to change anything. So when something undergoes gamma radiation or gives off gamma decay, it doesn't really change what the matter is, because this is just energy. So don't worry about seeing too much gamma radiation there in a nuclear equation. However, if we have an electron capture, okay, let's say I had iodine 123 is going to capture an electron. That means I have iodine 123, and that's 53. Okay, that means I'm going to capture electron, which means it's a reactant. It's before the arrow. So that electron comes before the arrow now because it's been captured by that iodine. Well, what's my product? 123, right? Because 123 plus 0 equals 123, right? And then I'm going to have 53 plus -1, or another way of putting it is 53 minus 1. I'll end up with 52. I look at the periodic table. I look for number 52. Remember, because number 52, this Z, is the atomic number. And that atomic number tells us what the element is. In this case, it's tellurium. All right? So, yet another example. This time we have a positron emission. Okay, emission, emit, emitted, emission, product. Okay, so emission and decay mean product. So in this case, I have sulfur 30. Sulfur 30 is going to undergo positron, is going to emit a positron. Okay, so if it's emitting a positron, it's a product. So I'm going to go ahead and write sulfur 30. Okay, remember that 16 comes from the periodic table. That positron is 0, 1, E. Okay, and then I look at my math, my top numbers. 30 is equal to 0 plus 30. Okay, 16 is equal to 1 plus 15. So my 15, 16. Yeah. Okay, so we're good. in this case, my element, if I find a periodic table, phosphorus. Okay, so the answer to what happens when sulfur undergoes positron decay or emits a positron, phosphorus 30 is produced. All right, and just for the fun of it, okay, because I think we have hopefully a good understanding of what went on right here, let's look at a combination. All right, what if I had carbon 14, okay, and it underwent electron capture and emitted 2 alpha particles. Okay, so let's take a look. Carbon 14, start off with how I have it, which would be carbon 14, and then I have 6 because that's 6 protons, and it has electron capture, which means that's an electron on the reactant side. Okay, and then I'm going to have some sort of product, but I'm also going to emit 2 alpha particles. Now there's 2 ways to do this. One of them is to do this okay, and there's my 2 alpha particles, and then I have my A, Z, X, okay? But another way you could write it, and it's completely up to you, is if I took those 2 and I wrote it as this, 2, 4, 2, HE, okay, and we put this coefficient in there, okay? It really means the same thing. If I have this 4 and this 4 up here and this 4 up here, that's 8. If I have this 4 times 2 is 8. 2 plus 2 on the bottom is 4. 2 times 2 on the bottom is 4. It really doesn't matter. Okay, you can do either one. I tend to do the coefficient, but you can write it out like I have it right here, and there will be no problem with it. So let's go ahead and take a look. Looking at my top numbers, 14 plus 0 is equal to 4 plus 4 plus A. Okay, and then my bottom number is 6 minus 1, or plus negative 1, right, equals 2 plus 2 plus Z. Okay? So in this case, I have 14 minus 8 is going to be 6. And then I have 5 minus 4, or excuse me, this is 5 over here, and we have 4 plus Z, right? That means Z would have to be 1, okay? This is a perfect example of me just making stuff up, okay? But it's really mattering of you being able to do the problem right, okay? Because I'm telling you right now, that thing right here, not going to happen, because you're never going to get 5 neutrons around a hydrogen proton, okay? But anyways, that's not entirely the point of the experiment, or the activity, as to whether or not this is really going to exist, but to set the problem up and solve for whatever this happens to be. Okay? So, if we have any questions, ask in class. You guys have a worksheet on this tomorrow. Okay? And then be sure to speak up. Okay? Don't sit there and be quiet and just let this part run by you, because again, like many things we do in chemistry, this isn't going to go away, right? We're going to stick with this. The next concept we do is going to be based on your understanding of how to solve and balance nuclear equations, because that's pretty much exactly what you're doing. You're balancing these nuclear equations. All right? So, have any questions? Let me know. If not, I'm ready for school tomorrow.